Hello, and welcome back to Introduction to CFD. I'm Professor Steve Miller. This class will be talking about a mathematical survey of critical equations and concepts for your success in this class. In the previous class, we talked about multiple kinds of computational fluid dynamics codes and their classifications. We talked about research versus commercial codes, serial versus parallel codes, meaning if they're running on a single processor or multiple processors, and a number of various types of codes and examples. We showed one type of example to illustrate the concept of an open source solver to look at solid shockwave equation. We looked at a number of flow visualizations that correspond to flows which we'll be looking at in this class in particular, like backward facing steps, jet flows, shear layers, and boundary layers. Finally, we looked at natural flow visualizations and compared them with computational fluid dynamics simulations as just an idea of a first way to compare simple flight tests qualitatively with numerical data. And it's a lot of fun. In this class, we'll be looking at a mathematical survey. In particular, we'll be looking at tensor analysis. Tensor analysis is critical for understanding CFD and its equations. So a lot of you probably haven't seen tensor analysis before. We'll look at the most critical elements in equations and summarize those in some tables near this part of the module. Then we'll look at some linear algebra concepts. Next, we'll look at classification of second-order PDEs, which are critical to understand the physics of computational fluid dynamics and fluid dynamics in general. We will in particular look at the wave equation, which is an equation which discusses how information propagates at a characteristic speed. In fluids, it's typically the speed of sound. And then the diffusion equation, which might be examined in a sense of how viscosity might work. Finally, we'll look at the Navier-Stokes equations, who the people are who created them, and of course, the famous Navier-Stokes problem. Let's now turn our attention towards tensor analysis, which is an area of mathematics and a way to manipulate equations, and most importantly for computational fluid dynamics, change coordinate systems. Tensor analysis is a systematic way for transforming quantities, in this particular fluid dynamic variables, from one coordinate system to another. We might write components of an n-dimensional vector x as x1 through xn, where n is the so-called dimension of the vector x. For example, in 3 dimensions, which is what we'll typically work with in computational fluid dynamics, or perhaps 2, you would have vector components x1, x2, and x3. This is probably very familiar for most students at this level. We would write these vectors as a bold symbol, bold x. Imagine we want to make a plane in space. Well, a plane in 3 dimensions can be written with the plane equation, which is shown by my cursor. A sub 1, x sub 1, plus a sub 2, x sub 2, plus a sub 3, x sub 3 equals c. Here, coefficients, constant coefficients, are a sub 1, a sub 2, and a sub 3. And then we have the constant coefficient c on the right-hand side of the equation. By changing a1, a2, and a3, and c, we're able to place a plane at any orientation and position in space. We might be able to write this equation compactly as one example with the summation symbol from I equals 1 to 3 for a sub I, x sub I equals c. So if we take the previous equation, you can see that we've written the left-hand side as a simple sum from 1 to 3. If we wanted to be in 2 dimensions, we would simply set the number of dimensions to 2 instead of 3. This can also be written in the so-called Einstein or index notation as shown on the bottom of the page. We might write a sub I, x sub I equals c. So going from the plane equation to the summation, which is most familiar to most students, to the summation equation is a pretty and fairly straightforward process. If we have 2 repeated indices in the equation in one particular term, it means that we sum them. For example, in this final equation, for the plane equation, we have 2 subscript i's. This would be summed from 1 to 3 if we're in 3 dimensions. The right-hand side, c, remains the same. For example, this equation would read just like the plane 3-dimensional equation, a1 x1 plus a2 x2 plus a3 x3 equals c. Let's look at this Einstein or index notation in a little more depth. The Einstein convention states that repetition of an index in a term denotes that the summation with respect to that index is over its particular range. So an index that is summed over is called a dummy index in that it disappears from the equations, and one that is not summed is a free index. So in the momentum equation, the Navier-Stokes equations, I would be the summed index. The ones that disappear would be j because they're dummy indexes. So these can be easily written with any variable. For example, in the center equation, the summation of I equals 1 to 3 of ai xi would be also equal to the summation of j equals 1 to 3 for aj xj. Let's look at one particular example of a free index where a unit normal vector is in 3D. If the unit normals in the x1, x2, and x3 direction are I1, I2, and I3, then the direction cosines alpha 1, alpha 2, and alpha 3 for the vectors n are a sub k equals the normal vector with the inner product, or dot product in this case, of the unit vector I sub k. So alpha sub k equals n inner product I sub k. This can also be shown in a different way. The dot product can easily be taken with itself, and as you should recall, and I hope that you remember, that the inner product in this case would result to 1. And you see this in the bottom equation, which you see is alpha I equals 1. In this case, we would simply be summing over I, which is the dummy index. Let's look at an example of the total differential for a function in 3 dimensions. Here have I written the equation dp equals partial p partial x1 dx1 plus partial p partial x2 dx2 plus partial p partial x3 dx3. These here represent derivatives, and these partial symbols where my cursor are for partial derivatives. For example, this first term on the right-hand side of the equal sign is the partial derivative of the static pressure in the x1 direction. That is x in the Cartesian coordinates. The total differential would be dp, which is of the pressure. So by summing the partial derivatives of p with their derivatives in each cardinal direction would yield the total differential of any function in 3 dimensions. With these tools, the index or Einstein notation, we can write them more compactly. So we can write this entire summation equation above as we did for the plane equation in the form here. We might write dp equals partial p partial xi dxi. What's the difference between the previous equation and the present one is the dummy index I, which we are summing over from 1 to 3. You should be able to expand this term out to the full form for any type of coordinate system. We might also look at this as the dot product of the gradient of p, or delta sup 2 delta squared of p. Then the component of delta squared p might be written as nabla p, and nabla is this upside down delta symbol of p sub I. So here the sub I or comma I of say partial p partial xi comma I, that would denote that we're taking the index notation and finding nabla p. You might find this type of term directly in the equations of motion. Here, partial p partial x sub I denotes that it's the partial derivative of static pressure in the I direction, and the comma I means that we're taking the partial derivative of the term. We can then take the divergence of a vector u. Divergence of vector u, which is velocity in fluid dynamics typically in terms of notation, is a very important term, especially for continuity. If nabla dot u, or the inner product of nabla and the velocity of vector u is 0, that is the so-called D'Alembert condition, meaning that the flow is incompressible. This might, and steady, mind you. This is often seen and imposed in incompressible Navier-Stokes solvers. We can write the right-hand side as simply the partial u sub I of partial x sub I. Once again, you see 2 dummy variables, I. This can also be written in a more compact form, which is often used by mathematicians studying partial differential equations. They might write u sub I comma I. This means that we have the velocity vector components I, and we're taking the partial derivative of it by common I. So what does that mean? We might expand that out as partial u partial x partial v, partial y, plus partial w, partial z for a Cartesian coordinate system of equations. Remember, if you see a single term with two dummy indexes, then you should be summing over them to the number of dimensions of your system of equations. We've looked at vectors, but we might also consider tensor analysis. We can also treat tensors by using the same type of subscript system, that is, the multiple subscript system. For example, let's define a particular matrix A, which I'll put in brackets, as this form in the first equation on page 7 of this class. We might write bracket A equals the bracket of the entire matrix. Those of you in mini algebra, and if you've taken linear algebra classes, have studied these forms of the equations and considered their analysis. We might write this compactly as A subscript ij. Now here, I denotes the row and j denotes the column. For example, A32 would represent row 3, column 2 element. A sub ij itself just simply represents a particular element of the matrix. Bracket A represents the entire matrix. Now, if we multiply A sub ij by, say, an m by n matrix B sub ij by a n by 1 column vector x sub j, then their product is a m by 1 column vector yi. We can simply write this equation in the linear algebra form as the second equation on slide 7. yi equals b sub ij xj. In this case, we might view, hey, xj is some n by 1 column vector, and b sub j is a matrix, and of course, y sub I is the resultant variable n by 1 matrix. This equation, if you look at it in index notation, and this is a very familiar operation, it's a matrix vector multiplication, which results in a vector, you'll see it is written as y sub I equals b sub ij x sub j. So this equation contains both a free index and a dummy index j. What does this mean? We can be free to select any variable I for any element in y sub I, and we're summing over j's, which disappear from the equation. So we would sum from j equals 1 to n in this case. Previously, we were just looking at 3-dimension summations. In this case, it's a summation over n. We can also now find the identity matrices. The identity matrices are very straightforward to find. Simply take any matrix, A or B or C, and multiply it by its particular inverse. We might write the inverse as A sup negative 1. So if we take A times its inverse, we'll get the identity matrix, which is the diagonal matrix with elements 1, and all off-diagonal elements will be, of course, 0. We can write this in a more compact form. We can write A sub ik times its inverse of k sub j, and here note the free and dummy indices in the equation. That's a good thing to practice, and you'll see it turns out to be the Kronecker delta function. We previously discussed what the Kronecker delta function is in this class, but now we can define it as a particular outcome of the multiplication of A with its inverse, in this example, any A, and it'll result in Kronecker delta functions. So look at this matrix in the lower right. We can write the Kronecker delta function in a 3x3 matrix example, but the dimensions can be arbitrary, it doesn't matter. It wouldn't be very much if it was just a single element, because it would just be 1, of course. And you can see any Kronecker delta function with ij of 1, 1, 2, 2, or 3, 3 will result in 1s on the diagonal. Off-diagonal terms will be equal to 0. This is actually a simple way to remember the derivation of the Kronecker delta function, or an alternative way to define it, other than just stating what the results are. Delta sub ij equals 1 when the subscripts I equals j. It is always 0 when I equals not j. This is a very simple way to remember it, and the way I prefer to. We can also now expand out if alpha I equals 1, like we've shown earlier. Alpha I, delta ij, alpha j. In this case, we essentially have two dummy variables because they both appear in the same term. If we expand these out, we get 1. In some way, this is interesting in that it's very much like the inner product operation for this variable. This is really a pre-multiplying of a 3 by 3 matrix by delta ij by the row vector alpha I, and then post-multiplying their product by the column vector alpha sub j transpose. We haven't looked at determinants, but now we have simple ways to look at determinants. Let's expand and find a determinant for a typical 3 by 3 matrix. You've probably learned about these expansions of determinants in a typical linear algebra class. Here we write the determinant as these two vertical bars instead of brackets around, say, a 3 by 3 matrix. Remember, we can find a determinant of a matrix of any order. Can you find a determinant of a matrix of, say, order 1000? Probably not by hand, but MATLAB and other computer programs which are running linear algebra prac essentially can trivially find these on a contemporary computer or even your cell phone. Anyway, it turns out the determinant of a 3 by 3 matrix can be written out as this multiplication and summation of elements. We have A11, A22, A33, plus the other element terms, etc. The way I remember it is to take the first element and find the determinant of the ones in the lower right corner. Then I subtract the second element and find the determinant of elements A21, A31, A23, and A33. And then I add the determinant of A13 itself, which is A13, times the determinant of A21, A31, A22, and A33. It's a simple way that if you just go across the first row and multiply by determinants not in that particular corresponding row and column, you can remember and find an iterative way to find any determinant of a matrix of any order. Let's write that in the Einstein or index notation in the bottom left. We write might det, meaning determinant of the matrix of a 3 by 3, as A sub ij, which will be equal to this notation where we've adapted for the matrices, just two vertical columns, A sub j, which is equal to epsilon rst ar1 as2 at3. Here I've introduced a new type of notation. Let's look at that. And this is an easy way, this permutation notation, to write determinants. Here, the permutation matrix, epsilon rst, is a tensor itself. We've defined it in a simple way over here on the right-hand side. Epsilon ijk, or rst, we can just replace the subscript variables independently, will be 1 if ij and k are cyclic. They'll be -1 if ij, k are anticyclic. And it'll be -1 if ij, k are anticyclic. And it will be 0 otherwise. Let's look at some examples. And by cyclic, I mean the order and values of the variables. For example, 1, 2, 3 would be cyclic. 3, 2, 1 would be anticyclic. Let's look at the examples where we have 1, -1, or 0. Epsilon, the permutation tensor 1, 2, 3, 2, 3, 1, and 3, 1, 2 are cyclic, meaning that these subscripts are appearing in numerical order of increasing value. Anticyclic means that these values are appearing in decreasing order. For example, 1, 3, 2, of course 1 and 3 are of increasing value, but 3, 2 goes down in value, so it would be a -1 value. Anytime you have 3 unique indices of 1, 2, and 3, then you can check their cyclic or anticyclic variable values. If you see any 2 of the 3 indices repeating, for example, epsilon 2, 2, 1, the 2 2's are repeating, then the value is 0. This actually comes out of a mathematical equation. We can easily put epsilon ijk anywhere, and it vanishes with the values of 2 indices being the same. For example, epsilon ijk when the indices are permutations of 1, 2, 3, and epsilon ijk of -1 otherwise. This means we can now write the cross product in a simple way between 2 vectors A and B. Here A and B are 2 particular vectors, and we've written the cross product in its typical form with sub I, What does this mean? We can expand this out and write it more compactly. It might seem more complicated at first, but you'll see the value of this later on in the class, I hope, as a permutation tensor of ijk times aj times bk. We can also rewrite the curl of any vector u. You might remember this, the curl, which is very valuable in fluid mechanics, and you probably remember learning about it in your Calculus 3 class, as nabla cross u. Curl is very much something like related to the vorticity of the fluid, which is a very physical quantity. It has to do with the rotation. We can now rewrite the curl of a vector u in a compact Einstein or index notation way. We might write the permutation tensor times the partial derivative of u sub k x sub j. That'll be equal to, if we simplify it, as epsilon ijk uk comma j. Remember here, comma j means the partial derivative of u sub k. K itself is a dominant variable, and so is j, because they are both repeated in the same term. So when we evaluate this equation, or this term on the right-hand side of the curl equation, we're actually retaining the subscript I from the curl. Remember, the curl operation of a vector u is a vector itself. So I represents the component of the vector, which can be seen on the right-hand side of the index form of the equation. Now that we have the permutation tensor and the Kronecker delta function defined, we can see how they are related, which is often used in CFD. On the last equation of slide line, I've written this particular identity, which is actually quite amazing. It's the permutation tensor of ijk times the permutation tensor of ist, mind you, t is not time, these are just indexes, subscripts, will be the Kronecker delta functions of js kt minus jt ks. And we'll see this used especially in the turbulence modeling portion of the course. Let's look at some basics of tensor analysis. Remember, the lowest ranked tensor is 0, and these will be scalars. Thermodynamic properties such as pressure and density are scalar quantities, and they might also be viewed now as part of the same system of tensor mathematics as the lowest rank. Tensors of rank 1 are vectors. That is, say, velocity vectors, vorticity, and of course, pressure gradients. Matrices are rank 2 tensors, which we've seen some here. Stress tensors, or Reynolds stress tensors, which we'll introduce later in the class, are of course rank 2 tensors. Example of these might be forces per unit areas or magnitudes with 2 associated directions. We'll see these appear in fluid dynamics and especially CFD. Rank 3 tensors and higher are rarely seen in computational fluid dynamics, but it's good to know that they're there. One example might be the permutation tensor, which we've just seen. Some properties of tensor analysis. Remember, a tensor is symmetric if, for example, a sub ij equals aj. That means the off-diagonal terms are equal to each other across the diagonal. For example, a12 would be equal to a21. Thankfully, many tensors in computational fluid dynamics and fluid dynamics in general are symmetric. This is an amazing fact which helps us reduce the number of equations we need to solve when modeling Reynolds stress and turbulence models. A tensor is skew symmetric if a sub ij equals negative ji. For example, in a 3x3 matrix, term a12 would be equal to the negative of term a21. It so happens that the rotation tensor, which appears in the equations of motion, capital omega sub ji, would be 1/2 of uij minus uj1. Notice the commas between I and j and I. This denotes the partial derivative operation. So this might mean 1/2 of the quantity partial ui partial xj minus partial uj partial xi. See if you can write that out and expand the terms. There'll be a lot of them. Now, remember, care must be taken when converting from the humble vector notation to Einstein notation. Einstein notation, index notation, were really used by Albert Einstein in some of his work to compactly write the equations of motion. They have been adapted by many communities to write and perform mathematics, especially in the field of fluid dynamics. If you remain in the field, it's good to get used to this type of notation. Let's look at these particular forms, just as a reminder. Nabla.u, which is the inner product with the vector u, might be equal to partial ui partial xi. Here the dummy variables are I. Sum them from 1 to 3 for 3 dimensions. U.nabla would be equal to ui partial xi. This is an operator term, and it might be operating on a velocity or a density times a velocity. You'll see both these terms appear in our equations of motion, which are solving in this class numerically. Part of the value of this work, of course, are coordinate transforms. We might imagine that we have a second coordinate system over line E and the first original E, which are 2 particular coordinates, and we need to determine the transformation rules for components of a vector. We'll define overline small e sub 1, overline e sub 2, and overline e sub 3 be orthonormal basis vectors of overline E. Then the 9 quantities defined by the dot product are the directional cosines. Here we would have a sub ij will be equal to e sub I inner product of overline E sub j. Here, a sub j will be the cosine of the angles between the I-axis and E and the j-axis in the overline E system. Furthermore, a sub ij will be the I component of the E system of overline E sub j. We can write based on these properties. Overline E sub j inner product E sub k equals E sub I dot overline E sub j times E sub I inner product overline E sub chi. This will be equal to a sub ij, a sub I k. So because vectors overline E sub j are orthonormal, we obtain these coordinate transforms, and they will be a sub ij, a sub ik will be equal to delta sub j k, and a sub ji, a sub ki equals delta sub j k. Now we can also write the vector x in the same way as E and overline E systems, but we'll have different components. We'll have x equals vector E sub I, x sub I, which is equal to overline E sub j, x sub j. These transformation rules are obtained by taking the dot product of this equation with the E sub k and overline E sub k. We can also differentiate with respect to xi the functions defined in E. I've summarized on this page these mathematical operations. Take a little bit of time and study this coordinate transform from, say, E1 to bar E1, and E2 to bar E2, and E3 to bar E3 in index and Einsteinian notation. Let's now summarize our tensor operations. There's addition, where we might add tensors. Here I've written some examples of second-order tensor addition. I've written product summarizations for the multiplications of first-order tensors and second-order tensors and third-order tensors, B. So in terms of components, we might write these as dijk, and it will be equal to ui b sub jk. So remember, in general, for tensor products of an nth order tensor and an mth order tensor is a tensor of order n plus m. Let us continue our summarization of tensor operations. Ordering of the suffixes are always important, but do not need to be the same in each particular expression. So for example, the ordering of the indices, the variable subscripts, will define different results. So in this case, we have the 3 same variables, d, u, and b. And we have subscripts, which are essentially the same, I, j, k. The only changes are their orders in these three particular terms. Can you try and figure out what these mathematical operations are? Finally, given a component of d sub ijk of a third order tensor, we might consider w sub k equals d sub iik. Here, w1, w2, and w3 will be components of the first order tensor. What does this reduction come to? Let us now summarize the inner products. If b and c are second and third order tensors, then their inner product is the third order tensor d. So d equals b inner product or dot product in 3 dimensions of c. We can write this, and you can see our reduction by replacing b and c, combining them with the Kronecker delta function, and then removing the simpler indexes. And you'll get e sub I, e sub L, e sub M, b ij, cj, L, M. It looks pretty complicated, but believe me, when you're changing coordinates in complicated sets of PDE, this will come in handy. We can also summarize gradients, which we might write as nabla with vector e sub I partial x sub I. Applied to a tensor field of, say, second order, we might write now b of x equals ei, ej, bij. Gradients of b is then the third order tensor h, which is given by this middle set of equations. So we might write h as ek, ei, ej, partial bij, partial xk. Or in terms of components, you might write h of kij equals partial bij, partial xk. And you can even write this in a shorthand way, which you'll often see in mathematical manuscripts in the group of partial differential equations. You'll see bijk for partial bij, partial xk. Sometimes people might drop the comma if they know something about the properties of the variable. So in general, the gradient of a tensor of order n is a tensor of order n plus 1. This is an excellent thing to remember. An example might be the gradient of, say, a scalar like pressure. Divergence will be a tensor, of course, b with the inner product of delta squared and b. For example, nabla inner product of b will be equal to the Kronecker delta function ki e sub j partial bij partial x sub k, which will be equal to e sub j partial bij partial xi. So remember, the divergence of an nth order tensor is a tensor of order n minus 1, which is opposite, of course, of the previous operation of the gradient, where you're increasing the tensor order of n plus 1. Think about it this way. You can increment the order of the tensor by applying the gradient and divergence operations respectively. It's an alternative way to think about the relations between the gradient and divergence of particular variables. The Laplacian is an extremely important variable in the theory of partial differential equations. It might be written nabla squared equals nabla inner product nabla, which will be equal to, in index notation, of the Kronecker delta function ij of partial 2 partial xi partial xj, or equal to, and this is seldomly written this way, I prefer the first form because the second one might be confusing to some readers, of partial 2 partial xi partial xi. One would never write partial xi squared in the denominator. That actually would mean a different mathematical operation, so be very careful about this fact. You might also expand in Taylor series some forms of the equations, but we won't be doing this too much in this class in index notation, but I put it there for your convenience. Gauss's theorem is also used in a lot of analytical fluid dynamics work, and we've written an index notation here for your convenience, but we will usually write this in the Cartesian form. But just for completeness of this talk, I've shown it here in the last equation on the slide. The divergence theorem can also be written by simply contracting I and k indices of the equations. There's also the vector cross product. Unfortunately, there's no equivalent to the so-called cross product or the curl. Remember the permutation tensor epsilon ijk, which we presented on a previous slide. We can now write the cross product in Einstein or index notation. For example, say we have some cross product vector from u and v, which we write u cross v will be equal to r. That should be equal to the determinant of the unit normal variables times their u and v vectors written on the second and third row. We can write this compactly now, and it should be obvious to you, I hope, that it will be epsilon, or permutation tensor, sub ijk of the unit vector components with sub I of j and k. Can you look at this equation and figure out which dummy variables remain? We can also write the components of the cross product in particular. For example, r sub I would be epsilon ijk uj vk. You can see that I is never summed twice on the right-hand side. Excuse me, it never appears twice on the right-hand side. For example, the first component of the cross-product vector from Einstein notation might be r1. We can write out the right-hand side from our definition of the equation up here, and we'll get u2 v2 minus u3 v2. For a vector field such as vorticity, which often appears in fluid dynamics, I've talked about in the visualization part of our class previously, and we'll look at derived quantities later on in the class on our visualization module. We'll write simply omega for the vorticity might be the component e sub I, so we would choose I equals 1, 2, or 3 for each component of vorticity omega of the permutation tensor epsilon ijk of partial uk, which is a velocity component partial xj. I've written capital U here because it might be an average velocity, or you can just think it as a velocity component for this time. We can write the components then, of course, by setting e sub I equals to say any value of the unit vector. And it would be omega I, and I've taken away the bold symbol here, which you'll see a lot in the class, to denote it's a vector component and not the vector which is bold. I've summarized from a book in these tables the operation, which you'll see in the left column, the Cartesian form in the second column, the Cartesian tensor suffix notation in the third column, and the matrix notation in the fourth column. Most students will, of course, be familiar with the Cartesian notation, or the so-called vector notation, in the second column. For example, inner product of two vectors will be u dot v. They're bold because they're vectors. The index notation will be written ui vi. So of course we sum over these values of I for the inner product, and we can also write these as in a matrix notation, which would result in, of course, a scalar quantity for an inner product. You can refer to this table in the rest of the class if you so desire, if you don't recall particular operations of index or Einstein notation. So it's probably one that's worth printing off and just keeping handy. Let's now change subject to classification of second-order partial differential equations. If you've taken a partial differential equations class, this will look very familiar to you. If you haven't and you're interested, there's many books on introduction to partial differential equations. Partial differential equations are a subject I'm passionate about. Their theory represents the underlying principles for the natural laws of our universe. A lot of the equations of motion that we believe dictate physics are written in the language of partial differential equations. There are three fundamental partial differential equations. For computational fluid dynamics class like this, we're going to look at two particular equations. First, we are going to look at their so-called classification. So we might consider, as in the first equation on this page, equation written in a general second-order way. This is a partial differential equation with coefficients a11, a12, a22, a1, a2, and a0. So these are constant coefficients. Their value dictates the classification of the PDE. Terms like u sub xx, uxy, uyy, etc. are the unknown values of u. Now, u sub xx would mean the partial derivative of u twice in the x direction. It would read partial 2u partial x squared. Similarly, uyy would be partial 2u partial y squared. Now, if we have a mixed partial derivative, it would read partial 2u partial x partial y. Remember, we would never write partial 2u partial x squared. Similarly, we have first-order partial derivatives appearing in the single equation. This term, where my cursor is, might be partial u partial x and partial u partial y. U, if no subscript, would just be u. They are all equal to 0. By setting these coefficients, we can change the nature and physics of the particular equation. What does it mean when we change these particular coefficients? Well, there's 3 types of cases that might appear. There's the so-called elliptic case, the hyperbolic case, and the parabolic case. For example, and this analysis is showed in partial differential equation books in introductions on the subject. I'm really summarizing the major results and not showing the detailed derivation. If A12, which is the coefficient in the second term, squared is less than the coefficients in the first and third terms of our basic general equation, then we might be able to reduce the entire equation to something like this, shown below. Partial 2u partial x squared plus partial 2y partial y squared plus the remaining terms is equal to 0. We call these terms with this property elliptic equations. We also call equations hyperbolic if a12 squared is greater than the multiplication, or in this case inner product, of a11 a22. That would be reducible to an equation in the form uxx minus uyy plus the remaining terms, which are equal to 0. Between the elliptic case and the hyperbolic case are when a12 squared is equal to a11 a22. It is irreducible, it is reducible to uxx plus the additional terms are equal to 0. Now, it just so happens if you can find the eigenvalues of this particular set of equations, then we can classify them according to these 3 properties. A partial differential equation is called elliptic if all the eigenvalues are positive or negative. A PD is called hyperbolic if one eigenvalue has the opposite sign and all the others are non-zero. A parabolic PDE is one where the eigenvalue is 0 and all others have the same sign. A PD is called ultra-hyperbolic if none are non-zero, but at least 2 are positive and at least 2 are negative. If you believe the coefficients are variables, then the equations might be elliptic in one region and hyperbolic in another. This might happen in the Navier-Stokes equations, because of course the coefficients might be changing depending on the speed of the flow. This is a little bit of a stretch to think about right now, but we'll see this. And these are critical concepts to think about if the flow is elliptic, hyperbolic, or parabolic. For example, a supersonic flow corresponds to a hyperbolic case. A subsonic flow corresponds to the elliptic case. And a parabolic flow corresponds to a transonic flow. We'll look at these physics and the connection between the Navier-Stokes equations and the speed of the flow later in the class. This is absolutely critical for the study of boundary conditions. One will need to know values of eigenvalues of the equations of motion, which are dependent on the current solution, if you will, to correctly set the equations of motion near the boundary of your computational domain. Let's look at one particular equation, which is one of my favorites. People have studied the wave equation for a long time. D'Alembert was one of the first people to find its solution through the so-called method of characteristics for the one-dimensional wave equation. Let's look at what D'Alembert did. For the wave equation, we might write, by setting particular coefficients in the previous page, UTT equals c squared uxx for the domain of negative infinity through x through positive infinity. This might be written as UTT minus c squared uxx of the quantity partial t minus c partial x times partial t plus c partial x operating on u equal to 0. This left-hand side and middle equation represent the wave equation operator. You'll notice that u sub t means partial 2u partial t squared. C is the speed of sound, in this case, or the speed of the propagation, squared. Uxx means partial 2u partial x squared. This is often replaced by the Laplacian symbol, an operator, for multiple dimensions. Here we're looking at a one-dimensional equation. This equation dictates the physics of, say, acoustics infinitesimal acoustics in a quiescent room. Quiescent means that the air in the room is stationary. We can write the general solution as u of xt, this means the unknown variable, as a function of position and time, as two arbitrary functions, f of x plus ct plus g of x minus ct. F and g are the arbitrary functions, c is the speed of sound, t is time, and x is the particular position where the solution is in space. In this case, it's one dimension. Now, like D'Alembert, we introduced the characteristics coordinates. Psi equals x plus ct, and eta equals x minus ct. You'll see the value of this characteristic coordinate system later and what it means physically. Now, through the chain rule, we might write partial x equals partial psi plus partial eta, and partial t equals c partial psi minus c partial eta. Through this operation, we have written the partial derivative with respect to x in terms of our characteristic coordinates. Therefore, through substitution, you might see that partial t plus c partial x equals 2c partial psi. Fascinating. And the governing equation now is in the different form. Originally, it was the wave operator on u of partial t minus c partial x of partial t plus c partial x of u. This is all equal to negative 2c partial psi of 2c partial eta of u equal to 0. We've rewritten our wave operator in terms of the characteristic coordinates. The characteristic coordinates are chosen because there's something physical known about the solution of the equations which they model. That is that the characteristic waves or disturbances in the flow will travel at ct and negative ct from an initial position x. Psi represents right-running waves in the one-dimensional system, and eta represents left-running waves in the non-dimensional system. That is, left-running would be in the negative x direction, and psi would represent waves or positions of disturbances in the flow in the right-running direction. You can see then, if we are taking the partial derivatives of u psi eta, that will be 0, and c is always non-zero. C must be usually physically some positive value. A positive value of c might represent the speed of sound. Typically in air, that's approximately 343 meters per second. The solution of the transform equation is then u equals the arbitrary function f of psi plus g of eta. These represent, in the solutions, families of characteristics that cross each other of x plus ct and x minus ct, respectively, for functions f and g. Down here, we've illustrated this solution approach of D'Alembert graphically. Along this x-axis might be time equal to 0. The y-axis is increasing time. For example, if we're x at this position, perhaps it's 1. With increasing time, disturbances are only located in solutions along these particular lines. These characteristics lines make up a characteristic net. This might be viewed as the so-called method of characteristics, which we discussed and taught in the compressible flow class, and it can be used for doing many things for more complicated equations, like designing a nozzle with the method of characteristics. This is the most illustrative and simple example of the method of characteristics in the field of partial differential equations. Many mathematical details have been unfortunately omitted due to time, but what I want you to take away is that in the wave equation, disturbances travel at the speed of sound in the different directions for this particular equation. Let's look at one example of the wave equation. Pretend that we have initial condition of phi. So everywhere in x at time 0, we have initial condition phi of x. And our initial condition requires for the solution the partial derivative of u at all times t0 at all x. We'll call that psi of x. And for time t0, we might imagine from our previous slide that the solution phi of x, the initial condition, phi of x, is equal to f of x plus gx. Now we can use the chain rule for psi x and rewrite psi x for the initial condition as cf derivative of x minus cg derivative of x. So these two equations, f and g, can be shown by differentiating and dividing by c. For example, phi prime will now be f prime plus g prime, and 1 over c psi will be f prime minus g prime. I divided both sides by c in this operation for your convenience and simplicity. So adding and subtracting the last pair of equations up here will yield f prime is 1/2 phi prime plus psi over c, and g prime equals 1/2 phi prime minus psi over c. We can then integrate these equations from the primes to find f and g as a function of some arbitrary variable s. Here we'll find 1/2 phi of s for f plus 1 over 2c integral from 0 to s phi plus a, and g, remember, which represents the derivative of the initial condition, will be 1/2 phi of s minus 1 over 2c integral sign of 0 to s phi plus b. Here a and b are the constants of integration, and a plus b must be 0 because to satisfy the initial conditions. Now we can substitute s for x plus ct into f and s minus x minus ct into g to satisfy the characteristics, and we'll find this bottom equation, which represents the general solution of the wave equation in one dimension. It'll be u of xt, that's the unknown variable, at any point in space and time, given the initial conditions phi and psi. That'll be 1/2 phi of x plus ct plus phi of x minus ct plus 1 over 2c, the integral of x minus ct plus to x plus ct of psi of s. So you can see, in particular, given any initial condition where we can find, and there exists some phi and psi, the derivative, we can simply find the analytical solution everywhere. Let's look at one example of the wave equation. Let's say we have an initial condition phi of x, and that will be equal to b minus b of the magnitude of x over a, and 0 for all other values of x greater than a. So b and a here are simply positive coefficients. This is the absolute value of x. This is essentially plotted at time 0 on the right-hand side of the figure. You can see that the initial solution is 0 everywhere except between the region of negative a as corresponding to the condition of the initial condition. You can also, of course, find the derivative of these values easily through analytical work. Now for between the values, of course, negative 3a over 2, and which is less than x, and negative a over 2, we might write in our particular analytical solution from the previous equation we developed. So we can find this analytical solution here, which will be u of xt, which will reduce to 3b over 4 plus bx over 2a. For the region of x less than a over 2, we'll also find this particular equation, which will be 1/2 b. So all we've done is define a simple initial condition, which represents like a little triangle disturbance in the fluid, and let time progress and see how it evolves in space. It's very easy to understand this once we look at the solution graphically. The top line here is the initial condition. The x-axis is x. You can see the initial condition is given by b. That's for x equals 0 from our equation on the left. Its height will be b. And later times, its initial width is spread out by a. So at a time a over 2c, a over c, 2a over c, and 3a over c, we see that this initial disturbance on our median spreads out and propagates in both directions. This is just like me or yourself speaking in a room, and the sound waves are spreading out in all directions at equal speeds. Study this solution graphically and see how it corresponds to the initial conditions of the wave equation. Let us now examine the diffusion equation, the second important partial differential equation we'll look at today, which shows some basic physics. The diffusion equation will be defined as partial u partial t equals k partial 2u partial x, defined over the whole range of x from time 0 to infinity. Its initial condition for all x at time t equals 0 will be phi. Now there's some properties of the diffusion equation. You'll notice that both these partial differential equations are linear, and they have interesting properties. For the diffusion equation, A translation of any solution, if you can find it, will be another solution. Any derivative of the solution is also a solution. Any linear combination of the solutions is also a solution. So the equation is linear, so if we find two different solutions, we can add them to find another solution. Finally, the integral of any solution is also a solution. Furthermore, dilatations of functions are solutions. For example, you can take the square root of a of x and find another solution. This is an amazing property of the diffusion equation. If you find one particular solution for one case, you can basically find infinite solutions from that particular specific solution, but it does not mean it's the general solution. So let's imagine that we will seek a particular solution which satisfies a construction of some special conditions. We'll call these Q. Q of x of 0 will be 1 for x greater than 0, and Q of x will be 0 for x less than 0. This is essentially setting a Heaviside function for the initial condition. A Heaviside function is a generalized function which has been explained and proved through the theory of generalized functions. This is a whole field of mathematics in itself, and so you're going to have to take my word for this type of idea. Now the solution will be non-trivial, so we can outline the steps to show the solution process. We will look for Q in a special form where G is a function of one variable. We'll let Q of x of t equals G of P, and let P equals x over the square root of 4kt. Now these ideas might seem a little bit arbitrary, but it comes out to the general solution of the diffusion equation. These were pioneered by mathematicians, especially in the 1800s. Now, we can try and convert our governing equations into an ODE for G through Q via the chain rule. Here, we show operations of taking the partial derivative of Q with respect to time and with respect to x. You'll see that we have this same kernel of x, or 1 over 4kt, where k is the coefficient and t is time, as a function of g prime of p. We can also find the second derivative of q with respect to x. It'll be 1 over 4kt g double prime of p. You'll notice that if we substitute qt and second derivative of q with respect to x into the original diffusion equation, we'll have it equal to 0 of qt minus k qxx. We plug in the variables from the right-hand side of these three sets of equations, and we'll get 1 over t, negative 1/2 p g prime p, minus 1 over 4 g double prime of p. I then showed that if you have g double prime plus 2pg prime, it will be 0 by showing the right-hand side equals left 0 on this previous equation. And now you can solve for g prime of p, which will be c1, a constant, times e to the negative p squared. So this is just simply a second-order ordinary differential equation. Through these substitutions and careful choice of q, we are able to insert them and reduce them and move them back into the original equation and solve a second-order ODE just like you did in your differential equations class. We've taken the complicated PDE and through careful substitution and choices of variables, which might be the solution, or some form of it, given that it's a linear equation in those properties, we found some form for q of xt, which is gp equal to c1 integral e to the negative p squared dp plus c2. So now we have two coefficients from our integrations. From this, of course, you can see that we found an explicit formula for q for t is greater than 0 and the initial condition. That's amazing. We can express these, of course, as a limit. If x is greater than 0, then it will be, our equation above will be 1 for time, limit of t going to 0, excuse me, the 7 is a typo, of q, which will be equal to c1 from this previous equation of 0 to infinity of e to the negative p squared dp plus c2. This will reduce to, as this integral is analytic, of c1 square root of pi over 2 plus c2. What a beautiful equation. Secondly, for the negative part of the x-axis, not 0, mind you, for the limit, we will have c1 integral negative p squared dp plus c2. This integral is also analytic, and you'll get negative c1 square root of pi over 2 plus c2. These coefficients are easily solved for c1 and c2 to satisfy the equations, and we'll find this equation for q over the whole x-axis for any time t of 1/2 plus 1 over square root of pi integral 0 to x over 4kt, square root of denominator, e to the negative p squared dp. Now that we found q, we need to define s, and we note that s is a property of the solution. We'll let s equals partial q partial x. Now we can define any function psi, little psi that is, and also define u. We'll let u of xt equals the integral from negative infinity over y, where y is a dummy variable and we left x for space, of s minus xyt and phi of y dy for t greater than 0. We need to verify this particular solution of their governing equations. Well, we know s, which is partial q partial x, and we know q now. We can substitute q in for s analytically, because we have a closed form solution for q, into this form of u. Once we do this, you can see that we can reduce it and find the simplified initial condition. U of x for time 0, we recover phi of x. Amazing. On the left, we have written the analytical solution from s to q. So we've verified that our equation satisfies the initial condition. Based on the initial condition for q, we know that the solution must vanish at infinity by looking at the equations. For example, look at s equals partial q partial x. It goes as 1 over 2 square root of phi kt e to the negative x squared over 4kt. Here you can imagine that as time goes to infinity, s must be going to 0. For example, e to the negative x squared over 4kt, where k is constant, t will become very large and this term will go to 0. Of course, t in the denominator becoming very large, even though it's a square root, will also be going to 0. So these terms go to 0 individually in the limit of time going to infinity. That's wonderful, and it means there's a very specific property of the diffusion equation, that no matter what initial condition we put in, the solution will be going to 0 for time going to infinity, or maybe not 0, a very small constant value. We can now substitute in the rest of our values and find a very compact general solution for u. U is our unknown variable, x is any spatial position, t is time. And we'll go as the coefficient 1 over 4kt, where k is like a heat conduction coefficient or diffusion coefficient. We'll go as the integral over the whole line, e to the negative x minus y squared times divided by 4kt times that initial condition phi of y dy. Y, of course, integrates away and we're left with x and t. So what makes s special in this whole method? It turns out that s is actually the Green's function. The Green's function was found by none other than George Green. Let's look at the one graphical solution of the diffusion equation. It might model mass, heat, or Brownian motion, which means about particle motion randomly moving in space. In this case, we might have a fluid and put a little bit of dye in it, and we can study in a laminar diffusion problem how that dye and its particle density moves through the fluids. So imagine at some initial time in some domain x, we have some dye concentration on the y-axis. And a very small or initial time, we might have some nice Gaussian initial condition centered about x equals 0. As time increases, that dye or concentration of the dye will be moving to the left and right, and it's removed from where it initially was. So this original Gaussian function might become smaller at some moderate time, and a large time it becomes smaller and smaller. You will notice, and this is what we call the maximum principle, that at no time will you have more dye in a location than you had previously. So if I had 1,000 units of dye, for example, or material at a position, I can never have more than 1,000 at a later time, according to the diffusion principle. This is the so-called maximum principle, that at one time you can never have more particles, for instance, at a later time at a particular position. The speed of propagation will be finite in the wave equation. It has some eigenvalues which represent, through the method of characteristics, the characteristic speed, which is c, the speed of sound in fluids. And the diffusion equation is essentially infinite, which is a little bit unphysical, mind you, that if I put some material in one location, the speed of propagation of that diffusion is essentially infinity. This is not physical, but we'll take care of this later in the class. Singularities do and can exist in the wave equations, and they're transported along at speed c. In nonlinear wave equations, this might represent a shock wave which travels faster than the speed of sound. This is absolutely possible physically. If there's a singularity at time 0 of a diffusion equation, it is immediately removed, and you have a continuous smooth solution at later times. So a diffusion equation will support a discontinuity immediately at time 0, but at all later times it's continuous. So think a diffusion equation as smoothing out solutions. If a wave equation might move a shock wave, a diffusion type of equation might smear it out and broaden it. The wave equation always has well-posed solutions at time greater than 0 and less than 0. Diffusion equations have well-posed solutions for times greater than 0. But unfortunately, the ideas of the maximum principle are demolished, and these equation solutions are not well-posed at time less than 0. The maximum principle in the wave equation does not apply. For nonlinear waves, you might have a steepening of the wave, and it could actually increase its amplitude in some situations in fluid dynamics especially. In the diffusion equation, there is the maximum principle, which I just discussed, but the maximum principle does not exist in the wave equation. Now, what happens when you have large times? For diffusion equations, it will decay to 0 if phi is integral, if the integral exists for the initial condition phi. For time, the energy is constant in this particular form of the wave equation. Linear wave equation conserves energy. For time 10 seconds or 10 million seconds, I should have the same amount of energy in the flow. This is not the case for diffusion equation if you're looking at something like an energy variable. You might think about wave equations as transporting waves through space, and this is unlike a diffusion equation which loses so-called information. For example, in acoustics, when I'm speaking, the waves are coming from my mouth to your ear, and they're being transported, and you can hear them. If the diffusion equation governed acoustics, the farther away you would be, the waves would be totally lost and go to 0, and we wouldn't be able to understand each other. So it's very fortunate that acoustics and our verbal communications are dictated by the wave equation. It's kind of just a funny thing to think about, but totally non-scientific and unphysical. Let's turn our attention to the Navier-Stokes equations. I explained these in a previous class, but we'll review them one more time here. The Navier-Stokes equations in this class will refer to the compressible form, generally in index or Einstein notation. Now that we've gone through index and Einstein notation a second time in the class, these should look very familiar to you. The Navier-Stokes equations will be, or some people might call these the hydrodynamic equations to be more precise, the continuity equation, which conserves mass, the momentum equation, which is essentially a vector equation, which conserves momentum, it's essentially Newton's law, and the energy equation, which conserves energy. This is essentially the first law of thermodynamics. Here, E naught will be an energy, and it goes as the specific energy plus the kinetic energy, UK over 2. Here, we have a dummy variable, K, so we sum over from K to 1 to 3 in 3 dimensions. So this will be U squared over 2 plus V squared over 2 plus W squared over 2 in the typical fluid dynamics framework. In the continuity equation, this might be partial rho partial T, where rho is the density of the fluid, U is the velocity of the fluid. Look at the second term here. This means how does rho times U change in space with partial derivatives? That might be expanded using index notation. Partial rho U, partial x plus partial rho V, partial y, plus partial rho W, partial z, where u, v, and w are components of the velocity vector. Here, this is how density changes with respect to time. That is, the derivative of density with respect to time is balanced, would be equal to the partial derivatives of rho and u in space. That would be nabla dot rho u in vector format. The momentum equation, the left-hand side should be familiar after explaining the continuity equation. The right-hand side, we have a pressure term. Once again, this is the Kronecker delta function, delta sub ij. So we would hold I, which is a variable for the conservation of momentum in the ith component, and we would sum over j. So this term would be, if we expand it out, in this particular equation, partial p partial x times 1 plus partial p partial x delta 1, 2, which would be 0, plus partial p partial x3 delta 1, 3, and delta 1, 3 would be 0. Recall the properties of the Kronecker delta function. Of course, this is all multiplied by negative. Tau sub ij, of course, is the stress tensor. Here's the energy equation. Q is a heat transfer rate, which might be thought of as something like the diffusion equation. The wave equation and the properties of waves are contained essentially in the left-hand side of the equations of motion and continuity and momentum. This is how fluids are convected and transported. In fact, both the wave equation and diffusion equation have properties in the Navier-Stokes equations, and the Navier-Stokes equations themselves, depending on the flow, could act entirely as an elliptic set of equations, a hyperbolic set of equations, and in very, very, very specific cases, parabolic set of equations. So it contains all the properties of all parts of differential equations. It's fascinating. Now the shear stress we haven't defined yet. We might write tau ij equals 2 mu sij, where mu is your first coefficient of viscosity. S sub ij sup star will be defined in the way on the right of this equation right here. So if you have an incompressible fluid, you might recognize this last term of S sub ij sup star. This is partial uk partial x k. This would be exactly nabla dot u. That's partial u partial x plus partial v partial y plus partial w partial z. If the fluid is assumed to be incompressible, this term would become 0 and it drops out of the equations of motion. That's quite wonderful. So that way it simplifies the whole set, which makes solving incompressible sets of equations easier. We'll also say that the heat flux term, Q sub j, goes as negative C sub p, first coefficient of viscosity, over the Prandtl number, which is also a coefficient, times partial T partial xj. Here, partial T is temperature. So this is where the temperature enters the equations of motion, especially when you have heat transfer, and it's in the direction particular j. Q sub j transfers to x sub j, which goes up and is summed over qj xj in the energy equation. Then there's the Prandtl number, of course, which we'll set as Cp times mu times 1 over lambda, and lambda is the coefficient of thermal conductivity of the fluid. These are the Navier-Stokes equations as we're going to usually look them in the class and how we want to solve them throughout the class. We'll make certain particular assumptions of these types of equations which we believe governs the fluid motion that we're studying in this class. Only in very, very high-speed rarefied flows would these equations break down generally in aerospace engineering, and we would have to turn to other techniques. The Navier-Stokes equations should have been derived and explained to you, at least in their incompressible form, in your aerodynamics or fluid mechanics classes. If they have not, please go back now and review their derivation in your fundamental texts, or go online and find some basic derivations through many, many papers. In fact, there's many ways to derive these equations, but this is the form that we'll be looking in index notation. This is often the form that's adopted in research and computational fluid dynamics in general. Now, the millennial problem in fluid dynamics and mathematics is one of the Clay mathematics problems. You can go to their webpage, which I've taken a screenshot of here, and they actually have a little picture of Stokes, which we'll talk about in a second. It's very interesting, and if you make mathematical contributions to the Navier-Stokes equations, which I'll outline what these contributions might be, you would of course get the Clay Mathematics Award and $1 million. And I've actually assigned this as a homework problem for fun, and you shouldn't be expected to actually do it, but you can just think about the problem and its difficulty. It's a challenge problem, and there's no currently known solution to these 4 things. Now, the Navier-Stokes equations were developed by none other than Claude Louis Marie Henri Navier, and he was born on the 10th of February, 1785, and he passed away on August 21st, 1836, and of course he was a Frenchman. He was an engineer and physicist who specialized in mechanics. He's known today to most people for the Navier-Stokes equations, and of course he went through the École Polytechnique, and in 1804 he completed his studies at École Nationale des Ponts des Chasseurs, from which he graduated in 1806. He constructed bridges mainly because he was a civil engineer. And you can actually go and see some of these bridges which still stand today in France. So if you're ever in France, you might accidentally drive across walk across one of his bridges in the countryside in some cities now and perhaps not even know it. If you go to the Eiffel Tower in Paris and look up, he is one of the names on the Eiffel Tower, which is quite a honor. He spent a lot of his life as a professor of calculus and mechanics at the École Polytechnique. George Gabriel Stokes was a very unique person and a Victorian. He was born on August 13th, 1819, and he passed away on February 1st, 1903. And of course, he was British. He spent his life doing work as a physicist and mathematician in fluid mechanics and optics and many other subjects. He was an esteemed mathematician, and I'm sure you heard his name under Stokes' theorem when you were studying Calculus 3, which is like a vector calculus usually in the United States. His name appears on the Navier-Stokes equations. It was really Navier and Cauchy who formalized the equations. Stokes used the equations to study pendulums and pendulum physics, and he's known for the famous Stokes flow problem where you have a sphere moving very slowly. A Stokes flow is a flow which creeps along at very slow speeds with a nonlinear term, and the Navier-Stokes equations drop out for an incompressible term. And he used these solutions to study swinging pendulums, and he formalized and understood the relations between the first and second coefficients of viscosity. That's Stokes' postulate, the relation between the first and second coefficients of viscosity. You'll notice that in the equations of motion which I presented, I did not show the second coefficient of viscosity because we used George Gabriel Stokes' postulate. That's really what he's known for. The equations were totally laid down by Navier originally. Perhaps we don't see Navier's original form of the equations today only because they were maybe written down in a non-intuitive way. It was really the mathematician Cauchy who put them in the form that we see today, and the reduction of the second coefficient as a function of the first was done by George Gabriel Stokes. Stokes really predicted the motion of pendulums moving very slowly and their decay using the Stokes equations, which were reduced from the full Navier-Stokes equations. He was an interesting person in himself, who is pictured on the right. He was indeed the president of the Royal Society, which still exists today. It's a society of scientific professionals, and if you're ever in London, you can go there and visit. He was there also the president of the Victorian Institute, and he was a staunch Victorian. He was a very, very conservative and religious person. And he tried to defend evangelical Christian principles against challenges from the new sciences, especially from this Darwin fellow. He did not believe Darwinian theory of evolution, especially because it went against Victorian ideas of Christianity and conservatism. He was also almost a confirmed bachelor his whole life, and he did marry a woman named Mary Susanna Robinson, who was a daughter of a reverend, and they had 5 children. But he didn't want to get married, and he wrote a many-page letter to her explaining to her why they shouldn't be married, and it turned out that she insisted they did, and of course, I think he lived a happier life for it. Let's look at the actual Millennium problem in fluid dynamics and mathematics. We won't read all this together, but you'll see from their PDF of Charles Pfefferman, which defines the problem, and if you solve any one of four of these particular problems on the right of the Navier-Stokes equations, which are defined in 1 and 2, you'll recognize these now in index notation. For example, here's the incompressible form, the momentum equation, with a body force F sub I, and the D'Alembert condition, the conservation of mass, and it has the particular initial conditions which we showed in a similar fashion for the wave and diffusion equation. So you should recognize these equations as the incompressible, time-dependent Navier-Stokes equations, and their closed form for pressure and velocity, given some constant coefficient viscosity mathematics problem. So there's actually 4 different things you can do. If you can do any one of these 4, then you would make a humongous advance in mathematics. And people have tried to do any of these 4 things for a long time and have totally failed. Some people have dedicated their lives to the study of this problem, and unfortunately they haven't found something that can be a proof of one of these 4 concepts. So if you want, you can go online and look at the Clay Mathematics website and see for yourself. In this class, we looked at index and Einstein notation and how that's applied through tensor mathematics and how it's related through basic summaries to the equations we'll see in this class. We don't have time to go through these derivations in an exhaustive way, but hopefully you find the time to look at something yourself. We then look at the solution and properties of the wave equation, diffusion equation. Finally, we looked at the Navier-Stokes problem. So next time, we're going to start a new module on computational grids and their generation. That will consist of approximately 3 classes. We will look at grid generation itself. What is a computational grid? We'll look at an overview of these computational grids. We will understand why we use computational grids in computational fluid dynamics. We'll make some notes on the discretization of the equations of motion like Navier-Stokes wave equation or diffusion equation and how it applies. Next, we'll look at the sensitivity of the equations. That is, the sensitivity of the grid generated from particular equations to create grids. We'll then look at one of the most important things for practitioners of CFD, which is the grid independent studies. We'll also look at different qualities or metrics for grids to understand why they're important. Thank you very much for your time. I'm Professor Steve Miller.